Hi everyone, welcome back to another one of our videos of becoming a ROS developer here at the Construct. My name is Rodrigo, and today we have one of our students, Pablo, who has completed his course of ROS Basics in C++. And now as a way of ending this course, he's done a project in which he controls a real robot here at our offices. So that's what we're going to be seeing today. So I'm excited to see the project. So hi, Pablo, how are you?
Hello, fine.
Great. So yes, as I said, whenever you're ready, you can start sharing your screen so we can see your project and you can explain us how you've done it.
Okay, so I'm going to share my screen.
Yes, please.
Up, here it
All
goes.
right, we can see it. We can see a
Uh,
presentation now.
okay, where is the? There is
All right, we
sorry. Um, okay, here. Where is the? So here we go. I have my all my code, and I have my main point dot launch dot py.
uh-huh.
I'm going to launch to show you the robot doing the circuit for wall following. So here it goes. So first the robot is going to search for the wall, the closest wall.
Mm-hmm.
It's going to approach to 0.3 meters from the wall, turn to start position, and then starts the wall following. So when the robot comes close to a wall in front, he's going to turn.
Mm-hmm. And what is this number we are seeing in the terminal?
So in the terminal, we're seeing the odometry of the robot.
Okay.
It's the distance from the beginning, from where it started to follow the wall.
Mm-hmm. So you kind of kept it within that outer ring for the robot to follow the wall, huh?
Yes.
Cool. And I also noticed something. Sorry, I'm gonna be interrupting you. It's just to clear out some doubts. So I noticed that it didn't go towards the obstacle, and it was closer to the obstacle in the beginning. Um, is there a certain algorithm yet you did to accomplish this?
So when the robot comes too close from the wall, it's going to try to go farther. As you can see, it tells too close from the wall, from the right wall. So
Right.
it's going to set an angular velocity to avoid the wall.
I see. So is the robot gonna stop when a lap is completed, or there, yeah,
Yes.
it just did.
Yes, when the robot comes back to the beginning, it's going to stop.
Great, and we see some output there too on the
Yeah, I only
terminal.
put the five first because it was a long list.
Right.
But we
Yes.
can see the different elements from a vector where it has the position and the angle.
Awesome. Well, that's a pretty clean job the robot did. Do you mind now sort of telling us how you did each one of these sections and divide them for us here?
Yes, I'm going to try to get back to my presentation.
Mm-hmm.
Up here it comes. Okay, so can I have my presentation, please? Okay. Well, it doesn't work pretty well with Zoom, so I'm going to do
So
it
just do it
this
like
way.
this. Yeah, just like this. It's fine. I'll resize the window.
So I'm going to explain you what I did, and my sequence diagram uh, disappeared, so it's not very practical.
Oh,
So I had a full sequence diagram that was showing how everything went by steps.
okay. So summarize it for us.
Um, so I had I have a main main file that launches three nodes
Yes.
that I wanted to show you, but the graph disappeared too.
Oh no.
There is a domain that launches three nodes, a main node that is the wall following nodes. That first calls a service node that is going to, as I said, search for the closest wall.
Mm-hmm.
This closest wall is found using the laser scans of the Turtlebot.
I see.
So it's going to search for the wall that is the closest, thanks to to four lasers, one in front, one on the left, one on the right, and one on the back.
Mm-hmm.
When the shorter laser is found, the robot is going to turn to the service node, is going to send a CMD-val topic to the Turtlebot to make it turn. Then when the robot turned, it when it finds that the front laser is the shortest, the the robot is going to go close to the wall until the laser it gets to 0.3 meters, and then it's going to turn on the left until it's the right laser that is the shortest. So here we're at the phase where the service made a service node made the Turtlebot come to the beginning position.
Mm-hmm.
Then it's going to start to go forward, and it's going to work as described here. So if the first thing that is checked is if there is a wall in front. If there is a wall in front, the robot is going to turn left when the wall is close to 0.5 meters. Else, it's going to try to stay between 0.2 and 0.3 meters from the wall. So if it's between those two distances, the robot is going to the node is going to send CMD-val instructions to go forward, only linear velocity. If it's too far, it's going to send an angular velocity to come closer to the wall, to come to the right. And on the other side, it's going to do the opposite.
Got it.
At the same time, this node at the beginning, before starting to go forward, it's going to call an action server, the third node that was created,
Mm-hmm.
and this node is going to record the odometry and send feedback. So when the the main node received the confirmation that the goal was accepted by the action server, the robot is starting to move. So to record the odometry, um, the we get the beginning position thanks to the odometry, and we start to move the robot. And each time we're going to measure the distance between the Turtlebot and to the beginning. And when the robot made the loop, and when it gets close to the beginning position, it's going to stop. So to avoid that the robot stops at the beginning because it's already at the start position, I put a condition so the robot has to do like 1 meter
Right.
before starting to look if it has to stop. And when it's close, to avoid the robot passing the beginning point, the starting point, I made a circle of distance. So if the robot goes on the left or on the right of the beginning point, the robot stops as well.
Right. And the bigger the circle, the easier it'll stop.
Yeah, but I tried to I made a small circle to avoid
That's possible. Right.
too much stopping too early.
Right. I get it.
So as I said, my code has one main node, a service server node, and an action server. And to communicate with those nodes, there are two custom interfaces that were created. One custom one service and one action message. So I had an RQT graph of the I can try to show you again. Okay. Well, I can't have it. I had the RQT graph to show you how it was, but
Right. So the nodes that would be in play.
yeah, I was trying to show as well that when the server node ended, the service node ended his service, it would unsubscribe to the laser scan topic to avoid having too many processes at the same time on the loop.
Right.
To avoid having too many processes at the same time. So I had some difficulties during the project, but most were found during the quizzes in the class, in the
Right.
ROS Basics class. So like the correction went pretty fast because I already had these problems. And all the elements of the project are inspired by the quiz codes because they're pretty similar. So the first problem that I found was finding the right laser angles because the how to say it because I didn't knew if the front laser was at index 0 or 90 or
Right.
180. And then when I went on the real robot, I found out that the lasers, the index of the lasers on the real robot were not the same as the simulated Turtlebot. So I had to put a parameter where I saved if it's the simulated Turtlebot or not. So when I change between the two environments, it changes the laser indexes. I also found that the Turtlebot hadn't the expected behaviors because when it got closer to the wall, because when it gets out of the range, the range capacity of the leader, the leader sent infinite or zero as values. So it was a problem with the how I coded the wall following. Also, there was the fine tuning of the velocities because I wanted to avoid having too many oscillations. Because as we have seen when my robot went on, when it's too far, I set an angular velocity, but when it gets to the point, it still has an angle, so it passes the right distance, and then it has to go back. So it goes left, right, left, right.
Yeah.
I had like some problems, like forgotten dependencies that were found because I built in. I don't stop building the package, so sometimes some dependencies were already there from a previous build, so it hadn't any problem. But when I erased all the environment, reset the environment, the build didn't found some dependencies. So it was one of my mistakes that took me some time to find the source, because why it worked well and then it stopped working correctly. In opposition to the class, the ROS2 class, I didn't made my custom interfaces in another package. I created I put the messages inside the package, so there are some specificities when it's done on the package XML and on the CMake list that have to be put. I also forgot to put a multi-threaded executor at the beginning. It was a problem that I have found in the class, because I thought just putting the callback groups inside of the class would make it multi-threaded, but I misunderstood it in the class, and it results even if you have the callback groups, you have to put the multi-threaded executor. Yeah. Also, it was long ago I made C++, so I hadn't the vector data structure in mind, and I wanted to do it with an array. And it was more complicated to do. So I had to check on the forum to find that I had to use a vector. And I also found out that when you create a custom message, you can have to put some dependencies on it. And I also forgot at the beginning to put the dependency on my action custom interface, the dependency on the point 32. And also I made a mistake I adopted the wrong strategy to determine if the robot was back at the beginning point, but I corrected it as I showed you. Um, Also, on my demonstration, we have seen that the robot started really parallelly to the wall, and that was a difficulty. When I started, the robot just turned until the right laser was the shortest. But the problem is that the Turtlebot stopped in BS like this. So when the robot started following the wall, it already was it already started with an angle. So it started to go far from the wall. So I had to use another strategy to make it start in parallel, making the central ray shorter than two other rays that are equidistant in angle.
You have 3 more minutes.
So I had a problem with this because I wanted just to use the next laser ray, but with the variability of the laser, the imprecision, these lasers would have the same values or are going to be shorter than the central one. So I had to make a graph with all the values, the range values, to check until what angle I can have the differences that I wanted. I wanted to show you the graph, but with Zoom it doesn't appear. So I'm going to pass. But if I had to do some upgrades to my project, I would use PID to optimize the robot's trajectory. And maybe I would use more rays to try to keep the distance to the wall. So thank you for your attention.
Great. Is that all your presentation? Yeah?
Yes.
All right. Awesome. Let me just kind of fix this here. Awesome. Congratulations. Really, really clear, Pablo. I really liked 2 things. How you described the difficulties you had, because a lot of the questions I had were related to that, and that you described what could go better with your project. So, but in general, really clear project, and you accomplished all of the tasks. So let me ask you a couple of questions. First, what happens if you call the service server when the robot is closer to an obstacle? Will it go to the obstacle?
Yes, that's a problem.
Okay.
It's why I will use more rays, because on the graph we will see that the obstacles have not the same form, or that the
Right. Okay, so you would use a strategy counting the points to avoid those. Just wondering. And I also was going to ask you, how did you prevent blocking callbacks? And you talked about how you were using callback groups, but forgot to use the multi-threaded executor. But because, yes, you need to have each callback group running in a separate thread in order for them to not block each other. So you address that. And the last question I wanted to ask you is, the robot runs in ROS 1. How were you able to communicate with your ROS 2 nodes if the robot only runs in ROS 1?
I made it interact with the robot in ROS 1 using the ROS bridge.
Great, yeah, because we didn't see it, so I just
Oh
wanted
yeah,
to make
uh,
sure that
I prepared it before.
that's actually better in my opinion, because we don't want to we only want to focus on the important things, but I just wanted to make sure of that. But yeah, other than that, those are all my questions. So congratulations, a really nice project.
Thank you.
All right, guys. So that's it for all of us here at the Construct. Remember, you can do these presentations to obtain a certificate in a lot of our courses. So I invite everyone that's watching to complete their projects like Pablo has done here. So thank you very much, and we'll see you next time. Bye-bye. Ok, listo.